Engineering education looks very different depending on where you study. In some countries, students enter highly specialized engineering programs immediately after secondary school. In others, students begin with broad foundational studies before selecting a discipline. Some programs emphasize theoretical mathematics and physics. Others focus heavily on hands-on design and practical application. Each of these models produce engineers, but they shape engineers in different ways, which raises an interesting question. How do different educational systems design the pathways into engineering? Welcome back to the EdTech Curio Cabinet. Hello again, I'm Christina, the Curio Steward. This season, we're exploring how education systems around the world structure learning. In earlier episodes, we examined global mathematics performance, examination cultures, and the Nordic model of teacher professionalism. Today, we turn to a particularly important question for STEM education. How do different systems design the pipeline into engineering and technical professions? Engineering education has always had to balance two important goals: deep theoretical understanding and practical problem-solving skills. Different systems resolve that tension in very different ways. Engineering education pathways vary widely across the world. In many European systems, students specialize early. Learners may enter a specific engineering discipline directly after secondary school and spend several years focused almost exclusively on technical study within that specific domain. In contrast, many North American universities follow a broader model. Students typically begin with foundational coursework, mathematics, physics, and often elements of the humanities, before specializing later in their undergraduate programs. This distinction reflects two different philosophies. One prioritizing early depth, the other building toward depth through a broader base. Education scholar William Wolff, former president of the National Academy of Engineering, argued that engineering education must prepare students not only to solve technical problems, but also to navigate complex social systems. That idea, engineering as both a technical and societal discipline, has shaped ongoing debates about how curricula should evolve. And for me, this isn't just theoretical. As an engineer by training, I experienced the North American model firsthand at the University of Waterloo, an institution globally recognized for its strength in mathematics and engineering. What stood out wasn't the rigor of the technical foundation, it was the layering. You built deep mathematical intuition. You learned to think in systems, but you were also constantly pushed to apply, to communicate, and to operate within real-world constraints. That interplay between theory and application wasn't incidental, it was intentional. Engineering education has always balanced two essential components: theory and application. Historically, many programs emphasize strong theoretical foundations. Students spent years developing fluency in mathematics and physics, understanding the principles that govern engineering systems before ever engaging deeply with real-world design challenges. The assumption was clear: first understand the rules, then apply them. But over time, many institutions began to recognize a limitation in that sequencing. Students often struggled to fully internalize abstract concepts without seeing how they functioned in practice. In response, programs increasingly began introducing design-based and project-based learning much earlier in their curriculum. Instead of waiting years to do engineering, students began engaging in hands-on design challenges, collaborative projects, and real-world problem-solving scenarios from the outset. This shift reflects a deeper insight. Understanding often strengthens when it's contextualized. Concepts become more than equations, they become tools. This connects directly to something we explored in Season 1, the hidden ecosystem of tools. In that episode, we discussed how modern engineering practice rarely happens in isolation. It exists within a rich ecosystem: simulation software, computational tools, collaborative platforms, and increasingly, AI-assisted environments. Preparing students for that reality requires more than theoretical knowledge. It requires fluency in applying that knowledge, applying it within systems that are dynamic, interconnected, and constantly evolving. And again, this mirrors my own experience. At Waterloo, the integration of co-op education reinforced this pattern in a powerful way. You weren't just learning concepts, you were cycling between learning and application repeatedly. Each work term reshaped how you understood what you had learned, and each return to the classroom deepened your ability to engage with new material. Engineering education naturally encourages specialization. Students develop deep expertise in specific domains: mechanical engineering, chemical engineering, computer engineering, and beyond. This depth is essential. It allows engineers to design complex systems, solve highly technical problems, and contribute meaningfully within specialized fields. But modern challenges rarely stay within the boundaries of a single discipline. Today's engineers are increasingly asked to work at the intersection of multiple domains: data science, material science, sustainability, software systems, and physical infrastructure. This creates a fundamental paradox. The deeper expertise becomes, the more important interdisciplinary collaboration becomes as well. In other words, depth and breadth are not competing priorities. They are interdependent ones. Engineering education must therefore prepare students who can go deep enough to contribute meaningfully, but remain flexible enough to collaborate across domains. Now, that balance is not easy to design, but is becoming increasingly essential. Across many universities, we are beginning to see a clear signal: the rise of interdisciplinary STEM education. Engineering students are increasingly engaging with areas like data science, entrepreneurship, public policy, and systems design. Institutions are recognizing that solving complex global challenges, climate change, infrastructure resilience, healthcare innovation, these all require more than technical expertise alone. They require systems thinking. They require communication across disciplines. They require an understanding of how technology interacts with society. And in many ways, this is not a departure from traditional engineering education, but an evolution of it. The core remains strong technical foundations, but the context is expanding. The engineers of the future may not just build systems. They may also be responsible for the ecosystems within which those systems operate. Engineering education offers a powerful lens into how societies prepare people to solve difficult problems. Some systems emphasize depth very early on. Others build towards it through breadth. Some prioritize theory first, and others integrate application from the beginning. But all of them are navigating the same underlying challenge. How do we prepare individuals to operate in a world where technology is constantly evolving and where the problems we face are rarely confined to a single domain? For me, reflecting on my own path through engineering and the foundation built at Waterloo, what stands out the most is not what we learned, but how we learned to think, to move between abstraction and application, to work across systems, to adapt. And those patterns continue to shape how we approach STEM education today. Education technology evolves quickly. New tools, new systems, new capabilities emerging all the time. But the patterns of learning, how we build understanding, how we apply it, how we connect ideas, change much more slowly. That's why we keep the cabinet open. Thanks for exploring the EdTech Curio Cabinet.